Okay, so we had started with module 4 IO interfacing. So basically entire this module we are going to deal with all the IO devices, input and output devices and the controllers and parallel buses, transmissions, serial transmission and IO software. So a very big chapter. So basically it is chapter 8 of Ascendant textbook. So we had started with the input devices. So first one we had studied keyboard and keypads and keyboards, right? So basically it is an matrix based. So you have the rows and the columns. So we are going to uh, initialize each column and we are going to check the rows which key is being pressed. All right. So basically scanning of the matrix there. So today we'll study the next input device. That is, have you drawn this figure, all of you? I had told you to draw this figure. Yes.
Yes, ma'am.
Okay. Next device, that is incremental encoder. So how does it works? An incremental encoder operates by generating two square wave signals that are of 90 degrees out of phase. So you can see there, the two signals are generated which are of 90 degrees out of phase. The signals can be generated either using an electromechanical contacts or using an optical encoder disc. So you can see there, an optical encoder disc is there. So whenever the light falls on that, so it is going to cut. So like this, the square wave is generated, right? A shaft and a disc is there. So, and you have the LEDs there. So whenever light falls on it, so what will happen? You will get a conducting period for that, right? So the signals can be generated either using an electromechanical contacts or using an optical encoder disc with the LEDs and photosensitive transistors. So even the photosensitive transistors are also used. So whenever the light falls, so during that period it will be conducting. So you can see there, operation of an incremental encoder, quadrature signal outputs from the encoder top, the signals. Optical encoder disc is there in the middle and disc and the optical sensor attached to the shaft at the bottom. So center shaft is there and then disc is there. So you can see the white lines and the black lines there. So as and when light falls on it, so that period is taken as the conducting period. So the square pulse is generated there, right? So like this, the incremental encoders are used. So the same thing is being written here. As the shaft rotates counterclockwise, the A output signal leads the B output signal by 90 degrees, and for clockwise rotation it lags by 90 degrees. So clockwise and anti-clockwise. So two signals are generated. The frequency of changes between the low and high on each signal indicates the speed of the rotation of the shaft. So that indicates the speed. So when we detect, this is what I did even in my PhD work also. So as I increase the rotation RPM, number of revolutions per minute, what will happen? The disk will either increase the speed or decrease the speed. Depending on that, I can control the speed of the motor there by using the PID controller. The same type of arrangement was used. So the frequency of changes between the low and high on each signal indicates the speed of rotation of the shaft. So when we detect the rising edge of the A signal, we examine the state of the B signal. If both is low, the knob has been turned counterclockwise. So we decrement the stored value representing the knob's position. If on other hand B is high and the knob has been turned clockwise, so we increment the stored value representing the knob's position. So depending on how it is being rotated. Depending on A signal and B signal, we are going to decide whether it is motor is running in clockwise direction or anti-clockwise direction. This is only the arrangement. Further, you need to connect this to the motor. This is only the shaft and the disc arrangement with this LED, right? Or even you can use photosensitive transistors also. So from this, the connection is being given to the motor. So like this, you can control the speed of the motor. Okay, so that's about the incremental encoder. So you should draw this figure when you come for the next class. One of the type of the input here. Then next, other analog inputs. So see here, what will happen? The signal generated is also a digital here. So digital, what all we studied, keypad and the incremental encoder. Even in keypad also, whenever the key is being pressed, the signal will be sent. So either high or zero, right? Next, what are the different types of analog inputs? So basically, see there, analog inputs. I was telling you an example of microphone in the last class. Analog input microphone and the analog output was a speaker, right? So many of you have joined today. I had given you the brief introduction like this only. So what I was telling, so you have your microcontroller or the microprocessor here, alright? So or else you can think of your FPGA, CPLD, anything, whatever you want, you can uh, think of the control part here. So whatever input is there, so I was telling you, and so input from the sensor, any of now from the keypad or encoder, whatever it is. So input, if it is a digital, our processor can understand. So input from the input transducers or sensors. You can use the transducer or a sensor. Then next, you can directly connect if it is generating a digital output. But if it is generating an analog, then in between you need a signal processing circuit here, that is analog to digital converter. So that digital data is fed to the microcontroller here. Like you can think, we had done one container example where we were monitoring the level and temperature. So level and temperature were monitored. All right. So if it is not an analog digital signal, then we need A to D. Then later that temperature was controlled. What we were doing further, if the temperature is going below or above, then it has to be indicated by an buzzer. Alright. So two containers were tested there. So the two containers were selected using an mux. 2 to 1 mux we had used. So two containers were selected, and finally if the level or the temperature is going out of range, then it is indicated by an buzzer. That means output side you have a buzzer there, right? So the same thing, output side also, if the output device or an output transducer uh, is in the form of digital, then digital output, whatever we are getting from the controller here, microcontroller or FPGA or CPLD, whatever it is, if we are generating in digital output, then if the transducer accepts the digital, if it is giving the digital output, then this is okay. Otherwise, again at the output side, you need again ulta of that, that is digital to analog converter. So the best example I was telling, so at the output sensor or the output transducer. So I was telling, this you can visualize your microphones. Your microphone is there inside at the input side, so which is generating the analog signal that is converted into digital and it is being given to the processor there. So your voice will be either modulated, right? modulated, and if any noise is there, all that will be removed, and that is finally sent to the speaker here, right? So speaker also wants the analog signal. So again, you need at the output side digital to analog converter. So basically, this is what we are going to study in this IO interfacing in this chapter, right? So basically, in module 4, entire this system control is there, input side A to D converter and an input sensor, and at the output side digital to analog converter and an output sensor or output transducer. So first we started studying with the input devices. So first one, keypad controller is over, then next actuators. Then now these two are digital. Now we are going to study the different types of analog inputs. So what are the other different types of analog inputs? So keypads, knobs and position encoders over. The next analog inputs. So first one is microphone. First one is microphones. These are among the most common sensors in our everyday lives and are included in digital systems such as telephones, voice recorders, and cameras. The movement of the plates together, plates are being used and apart in response to sound and pressure creates the detectable voltage across the plates that varies the sound and that varies the sound pressure. Right. So how the microphone works internally, right? So that's how the microphones are working. The next other type of analog inputs, accelerometer, used for measuring the acceleration and deceleration. A common form of accelerometer used in automobile airbag controllers as a microscopic cantilevered beams manufactured on silicon chips. So these are the other type of accelerometers, other type of analog device, that is accelerometer. We are not concentrating much into details of this. Next, fluid flow sensor. Fluid flow sensor, third one. So two matched. So how internally it is being designed is being just told. Two matched resistors are self-heated using an electric current. One of the resistor is placed into the fluid stream. So out of two resistors, one is placed into the fluid stream, which cools it by an amount dependent on the flow rate. Thus, the flow is measured. Since the resistance depends on the temperature, so resistance is dependent on the temperature. The difference in the resistance between the two resistors depends on the flow rate. So resistance value will give you the flow rate. The resistance difference is detected to device on an analog input signal. Right? So using the resistance value, flow rate is detected here. The next, gas detection sensors, another type of analog device, a photoionizing detector. This is nothing but it is a photoionizing detector, uses ultraviolet light. So this is going to use an ultraviolet light to ionize the sample of the atmosphere. Gas ions are attracted to the plates that are held at the potential difference. So the circuit path is provided for charge to flow between the plates. Right? So that's how it is going to detect. So ultraviolet light is used here. Next, analog to digital converters. So if you get this question, so other analog inputs, what all we have studied, the other analog inputs could be from the microphones, accelerometers, fluid flow sensors, gas detection sensors. Like that, you can go on naming a number of analog inputs are there. Just for your information, these are being given. basically this chapter, general question, what are the different types of input devices, so you can just list and give the details. Directly next you will get the question for different types of analog to digital converters. So as I was telling, the first figure, this figure is very important, so we have to note that. That is what uh, uh, first block will be input sensor, then next A to D converter, then after that, so this is the input A to D converter, then you have your microcontroller, any controller here, right? Then you have D to A converter, and finally the analog output is given to the output transducers. So you can just take the screenshot of this. This is very important. So finally you have the output here. So the basic diagram of a controller. So now we studied some of the input devices. Keypad, first one was keypads and this. Then next accelerometer. Then next another 3 to 4 different analog devices. So next we are going to study analog to digital converter. If the sensor is directly giving the digital data, then there is no requirement of A to D converter. So directly it is given to the microcontroller. If it is generating an analog signal, which our controller doesn't understand, that's why we need the analog to digital converter. So the analog data will be converted to digital value, and that is given to the controller. So some action will be taken place. Like I was telling, if low level and the temperature, if it is high, then what has to be done? So they will be controlled in the microcontroller here. So only if the signal generated from the input device is an analog signal, then we compulsorily need A to D converter. So this is what we are going to study now. What is analog? What are the different types of analog to digital converters? Hope already you have studied this in digital class. Have you studied different types of A to D converters?
Yes, ma'am.
Okay. So then quickly we can go through the different types of A to D converters. What are the different types of analog to digital converters? Can anybody tell me ADC's types? What type of ADC you studied? Any one of you remember that? What is the type of ADC that you have studied? Hmm? Sandhya, Ankita, Vaishnavi, Akash, Vinay, ಯಾರು ಆನ್ಸರ್ ಮಾಡ್ರಿ, ನೆನಪೈತಾ A to D ಕನ್ವರ್ಟರ್ ಯಾವ ಟೈಪ್ ಓದಿದ್ರಿ? Hmm? Do you remember or no? Are you able to hear me?
Yes, ma'am.
ಆಕಾಶ್ ನೆನಪದವ ಯಾವಂತ? So analog to digital converter. Have you heard of flash ADC?
Yes, ma'am.
So you can see there what is being done. So analog value have to be converted into digital value. So analog input signals from the sensor need to be converted into digital form so that they can be processed by the digital circuits and embedded software. So if it is, so as you all know, our controller cannot process the analog signal. So that's what he is telling here. Analog input signal from the sensors need to be converted into digital form so that they can be processed. So they can be processed by the digital circuits. Basically, your processor. It could be a processor, it could be a controller, or our CPLD, or our FPGA, anything. DSPs ನೋಡಿದ್ರೆ TMS 320 ಇರಬಹುದು, right? So anything it could be, and embedded software. So the basic element of an analog to digital converter ADC is an comparator. Nodrally. Basic concept analog to digital converter mainly you are going to use a comparator. So compare ಮಾಡ್ಕೊಂತ ಹೋಗ್ತಿರಲ್ಲಿ. So whether it is equal to 5 volts of value, then next for 4 volts, next for 3 volts, like that, you are going to compare there. So the basic element of an analog to digital converter ADC is a comparator. A comparator senses whether an input voltage. So V in, see there, the input voltage is there. That V in is connected to the plus of the comparator, right? Plus sign of the comparator. Then the comparator senses whether ಇದನ್ನೇನಂತಂದ್ರೆ ಇವೆಲ್ಲ ಯೂಸಿಂಗ್ ಒಪ್ಯಾಂಪ್ ಕಂಪ್ಯಾರಿಟರ್ ಎಲ್ಲ ಮಾಡಿರಲ್ಲ ಎನಲಾಗ್ ಕ್ಲಾಸ್ನಾಗೆ AEC ಕ್ಲಾಸ್ನಾಗೆ.
Yes, ma'am.
So comparator senses whether an input voltage, that is which is connected to the plus terminal, is above or below the reference voltage. ಒಂದು ಇನ್ನೊಂದು ರೆಫರೆನ್ಸ್ ವೋಲ್ಟೇಜ್ ಇಟ್ಕೊಂಡಿರ್ತದೆ VF, ರೈಟ್. ಸೊ ನೋಡ್ರಿ ಇಲ್ಲಿ ರೆಫರೆನ್ಸ್ ವೋಲ್ಟೇಜ್ ಎಲ್ಲ ನೆಕ್ಸ್ಟ್ ಪ್ರತಿಯೊಂದಕ್ಕೂ ರೆಫರೆನ್ಸ್ ವೋಲ್ಟೇಜ್ ನೆಕ್ಸ್ಟ್ ಕಂಪ್ಯಾರಿಟರ್ಗೆ ಹೋಗುತ್ತನೆಗೆ ಇಟ್ ಈಸ್ ಗೋಯಿಂಗ್ ಥ್ರೂ ಎ ರೆಜಿಸ್ಟರ್. So always when it goes for the next one, there will be an voltage drop here, right? So finally it is connected to the ground here. So the whatever voltage available at this comparator is different, at this comparator is different, illi bere, illi bere, illi bere, because the voltage drop is different at all the other inputs there. So V in and V reference are compared there. The comparator senses whether there is an input voltage to the plus terminal is above or below the reference voltage, which is connected to the negative terminal, and outputs either 1 or 0 accordingly. So encoder use ಮಾಡಿ finally the output will be either 1 or 0 here accordingly, right? So that is the basic concept of A to D converter, right? The simplest form of ADC is a flash ADC. A converter with n input bits. Here, this is very important. A converter with n output bits consists of a bank of 2 to the power n comparators. So this is a very important. N output bits ittantandre analog to digital ಈಗ 8 n ಎಷ್ಟು ಇರ್ತೈತಿ 4 bits 8 bits 16 bits depending on that. So 2 to the power n minus 1 comparators are needed. So a converter with n output bits consists of a bank of 2 to the power n minus 1 comparators that compare the input voltage with the reference voltage derived from the voltage divider. ಅಲ್ಲಿ voltage divider circuit ಐತಿ, ಹೌದಾ ಇಲ್ಲ? ಈಗ voltage divider circuit ಹೆಂಗ್ ವರ್ಕ್ ಆಗ್ತದೆ? If I take R1 and R2 are there, right? If the main voltage Vin is applied here, so what is the output voltage across this? If this I write as V1 and if I this write as V2, what is V1 voltage equal to? Can anybody tell me? Compulsory 1 mark extra. ಯಾರ ಹೇಳಿದ್ರು? voltage divider circuit, current divider, voltage divider ಮಾಡಿರಿ. What will be V1 equal to? ಹೆಂಗ್ ಕಂಡುಹಿಡಿತೀರಿ? V1 V2 equal to what? ಹೆಂಗ್ ಕಂಡುಹಿಡಿತೀರಿ? R1 R2 is there and the main voltage Vin is there. Can anybody tell me?
Vn divided by R1 plus R2.
Divided by R1 plus R2. What should be there in the numerator?
Vn ma'am.
Vn. ಮತ್ತೇನಾದ್ರೂ ಬೇಕಾ ಇದ್ರ ಜೊತೆಗೆ? Vn ಇಂಟು ಬರೀ Vn ಅಷ್ಟೇನಾ?
V2 ma'am.
ಕರೆಕ್ಟ್ ಐತಿ, ಆಲ್ಮೋಸ್ಟ್ ಮ್ಯಾಕ್ಸಿಮಮ್ ಇದು ಕರೆಕ್ಟ್ ಐತಿ. Vn ಇಂಟು
V2.
ಅಲ್ಲ, V2 ಬರೆದ್ಬಿಟ್ರೆ ಎಲ್ಲ ಅನ್ನೋನ್ ಆದ್ವಲ್ಲಮ್ಮ. ನನಗೆ Vn ಗೊತ್ತೈತಿ, R1 R2 ಗೊತ್ತೈತಿ, ನಾ V1 ಕಂಡು ಹಿಡಿಬೇಕೀಗ. ಇದು ಏನಿರ್ಬೇಕು? ಯಾರು ಹೇಳಿದ್ರೆ ಆನ್ಸರ್?
I'm
Who
Sandhya,
told
ma'am.
this? Sandhya. V in by R1 plus
Sandhya,
R2.
ma'am.
V2 ಅಲ್ಲ ಇದು. This has to be the
V2 R1, ma'am.
opposite resistor R2. Whereas for current divider rule, same resistor. Current divider ಗೆ same resistor and opposite resistor. Current divider ಗೆ V1 into R1 ಅಲ್ಲ, V1 into R2 divided by R1 plus
Same
R2 will
resistor.
give you ಸೇಮ್ ರೆಜಿಸ್ಟರ್. ಇದು ಒಂದು ಚೆಕ್ ಮಾಡ್ಕೊಳ್ರಿ. ಕರೆಂಟ್ ಅದೇ ಕರೆಂಟ್ ಡಿವೈಡರ್ನಾಗ ಅಪೋಸಿಟ್ ರೆಜಿಸ್ಟರ್ ಏನು ಅಲ್ಲ, ಕರೆಂಟ್ ಡಿವೈಡರ್ನಾಗ ಅಪೋಸಿಟ್ ರೆಜಿಸ್ಟರ್ ಕಾಣ್ತೈತೆ. So that's how we are going to. So now you know the main V in, you know, V in, think now I have the analog voltage as 5 volts. Then next I have used the voltage divider there. N number of resistors are being used. Right? So whatever the drop will be there, that is connected to the comparator. So whether the input voltage 5 and 4 are compared, depending on that, the output is generated, which is greater and lesser. So that's what I was telling. I'll clear this. Okay. The simplest for, okay, this we did. This, so if you have n output bits, you need to generate, then you need 2 to the power n minus 1 comparators are required. This is very important, that compare the input voltage with the reference voltage derived from the voltage divider network. So that's how the voltage divider works, what I told. For a given input voltage, so V in is K times Vf, that is the reference voltage into K, where Vf is the full scale voltage and K is the fraction between 0.0 and 1 there. So that is the K fraction. The proportion K of the comparators have their reference voltages above V in, and so the output is 1. Above V in ittandre 1. And the remaining comparators have their reference voltages lower than V in, and so the output is 0. So like this, each voltage is compared and either 1 or 0 is generated there. Okay, flash ADCs have the advantage. So what is the advantage of the flash ADC here? Flash ADCs have the advantage that they convert an input voltage to a digital form very quickly. So this is the advantage of the flash ADC. High speed flash ADCs can perform tens or hundreds of millions of samples per second. So at that fast rate, the samples are converted and so are suitable for converting high bandwidth signals such as those from the high definition video cameras. Antalella, it will be converted into digital. Such cases, such applications, they are being used. So such as those from high definition video cameras, radio receivers and radars. So these are the examples. Their disadvantage is that they need a larger number of comparators. ನೋಡ್ರಿ ಇದೆಲ್ಲ ಆಗಕತ್ತೈತೆ, ಬಟ್ ಜಸ್ಟ್ ಒಂದು 8 ಬಿಟ್ಟಿಗೆನೆ 8 ಕಂಪ್ಯಾರೇಟರ್ಸ್ ಇಷ್ಟು ರೆಜಿಸ್ಟಿವ್ ನೆಟ್ವರ್ಕ್ ಬೇಕಾತಲ್ಲಿ. ಸೊ ದಟ್ ಈಸ್ ದ ಡಿಸ್ಅಡ್ವಾಂಟೇಜ್. ನಮ್ದು ಏನು ಏಮ್ ಇರಬೇಕು, ಲೆಸ್ ಸ್ಪೇಸು ಇರಬೇಕು, ಸೊ ಹೈ ಸ್ಪೀಡು ಇರಬೇಕು. ಸೊ ಎಲ್ಲೋ ಒಂದ್ ಕಡೆ ಯು ಹ್ಯಾವ್ ಟು, ಅದನ್ನೇ ಮತ್ತೆ ಜಾಸ್ತಿ ನವಡೇಸ್ ಇವನ್ 8 ಬಿಟ್ ಕಂಪ್ಯಾರೇಟರ್ಸ್ ಅಲ್ಲದೆ ಇವನ್ 16 ಬಿಟ್ ಎ ಟು ಡಿ ಕನ್ವರ್ಟರ್ಸ್ ಎಲ್ಲ ಅದಾವು. ಬಟ್ ಅಗೇನ್ ಸರ್ಕ್ಯೂಟ್ ಡಯಾಗ್ರಾಮ್ ಇದನ್ನೆಲ್ಲ ಹಾರ್ಡ್ವೇರ್ ಎಲ್ಲ ಇನ್ಕ್ರೀಸ್ ಆಗ್ತದೆ ಅಂತ ಹೇಳಿ ಮಿನಿಮಲ್ ಬೆಸ್ಟ್ ಈಸ್ 8 ಬಿಟ್ ಅಂತ ಹೇಳಿ ವಿ ವಿಲ್ ಯೂಸ್ 8 ಬಿಟ್ ADCs only. So their disadvantage is that they need large number of comparators. Hence they are only practical for ADCs that encode the converted data using the relatively small number of bits. So small number of bits ಅಂತಂದ್ರೇನು ಇದನ್ನ ಏನಂತಂದ್ರ 8 bit only is best suitable. So here one of my research scholar, PhD scholar, he is designing analog to digital converters using cadence tool, but he is doing 8 bit only. But ಇದನ್ನ ಏನಂತಂದ್ರ 45 nm ನಾಗೆ ನ್ಯಾನೋಮೀಟರ್ ಇದ್ರಾಗ ಡಿಸೈನ್ ಮಾಡಕತ್ತಾನಪ್ಪ. ಬಟ್ ಓನ್ಲಿ ಫ್ರಂಟ್ ಎಂಡ್, ಬ್ಯಾಕ್ ಎಂಡ್ ಅಲ್ಲ, ಅಪ್ ಟು ಸಿಮ್ಯುಲೇಷನ್. ಸೊ ವೆರಿ ಗುಡ್ ವರ್ಕ್ ಹಿ ಹ್ಯಾಸ್ ಡನ್. That is what implementation of ADCs using cadence tool he has done in 45 nm. Right. Then next, so that is regarding the flash ADC. Compulsorily this question will come for 10 to 12 marks. So directly 10 to 12 marks, what are the different types of analog to digital converters ಅಂತಂದ್ರೆ ಫ್ಲಾಶ್ ಎಡಿಸಿ, ಸಕ್ಸೆಸಿವ್ ಅಪ್ರಾಕ್ಸಿಮೇಷನ್ ಎಡಿಸಿ ಎರಡು ಬರಿಬಹುದು. ಇಲ್ಲದ್ರೆ ಅದು ಯಾವ್ದಾರ ಒಂದು ಕೊಟ್ಟು ಮತ್ತೆ ಎಕ್ಸ್ಪ್ಲೇನ್ ದ ಇನ್ಪುಟ್ ವೇರಿಯಸ್ ಇನ್ಪುಟ್ ಡಿವೈಸಸ್ ಅಂತಾನೆ ಒಂದು 6 ಮಾರ್ಕ್ಸ್ ಕೊಡ್ಬೋದು. ಅವಾಗ ಉಳ್ಕಿದ್ದು ಎಲ್ಲ ಸ್ಟಾರ್ಟಿಂಗ್ ಏನು ಸ್ಟಡಿ ಮಾಡಿದ್ವಲ್ಲ ಅದನ್ನೆಲ್ಲ ನೀವು ಹೇಳಬೇಕಾಗ್ತದೆ. ಸೊ ದಟ್ ಈಸ್ ರಿಗಾರ್ಡಿಂಗ್ ದ ಅನಲಾಗ್ ಟು ಡಿಜಿಟಲ್ ಕನ್ವರ್ಟರ್ಸ್. ನೆಕ್ಸ್ಟ್ flash ADC. Then next is successive approximation ADC. So you can observe here what all is there. Successive approximation ADC, SAR register is there, clock starter, then digital to analog converter, then DAC is there here, V in and V reference. That we will see how it works. Successive approximation ADC ಓದಿರಾ? Have you studied this, all of you?
Yes, ma'am.
Flash ADC, successive approximation ADC. 1 ನಿಮಿಷ. 16 members again, 18 were there. ಯಾಕೆ ಬರ್ತಾ ಇಲ್ಲ? So successive approximation ADC used for signals that change more slowly. So for such applications, we are going to use successive approximation ADCs. Where flash ADCs are used, that we have done the listing there, right? It uses a digital to analog converter. So DAC is used here, digital to analog converter internally, to make successively closer approximations to the input signal over several clock periods. So internally D2A converter is used. So when start input is activated, the successive approximation register SAR, see there. So for SAR, what all signals are going there? Start and clock. So V in analog signal, this reference signal is connected to the comparator, then VF analog through the DAC, right? So finally you have D out and done bit, right? So used for signals that change more slowly. So it uses the digital to analog converter DAC internally to make successively closer approximations to that of the input signal. When start input is activated, the successive approximation register SAR is initialized to the binary value, first one 0, then rest all highs. This will be initialized to SAR. This value is provided to the DAC. So from SAR, this value is given to the DAC there, right? So it is given to the DAC, which produces the first approximation just less than half of the full scale voltage. ಅಂದ್ರೆ ಅರ್ಧ ಅರ್ಧ ಮಾಡ್ಕೊಂತ ಹೋಗ್ತದೆ ಅದು, half, then next quarter, like that. So 1 is there, then next half, then next 4 values, then next 8 values. So like that it is going to compare. This value is provided to the DAC, which produces the first approximation just less than half of the full scale value. The comparator compares this approximation with the input voltage. Whatever the DAC output is there, that and the input voltage are compared. If the input voltage is higher, the comparator output is 1, indicating that the better approximation would be above the DAC output. If the input voltage is lower, the comparator output is 0, indicating that the better approximation would be below the DAC output. So it will give you the next below DAC. So SAR ಏನ್ ಮಾಡ್ತತಿ, ಇನ್ನೊಂದು ವ್ಯಾಲ್ಯೂ ಕೊಡ್ತೈತೆ ಅವಾಗ. The comparator output is stored as the most ಹೆಂಗ ಕಂಪ್ಯಾರಿಟರ್ ಔಟ್ಪುಟ್ ಏನ್ ಜನರೇಟ್ ಆಗ್ತದಲ್ಲ ಅದು ಹೊಳ್ಳಿ ಮತ್ತೆ SAR ನೆಗೆ MSB ಅಂತ ಸ್ಟೋರ್ ಆಗ್ತಂತ ಹೋಗ್ತದೆ. The comparator output is stored as the most significant bit in the SAR and the remaining bits are shifted down one place. ಒಂದಾದ್ಮೇಲೆ shift ಆಗ್ತದೆ. So this gives the next approximation, that is a D7. ಮತ್ತೆಲ್ಲ ಆಸ್ ಇಟ್ ಇಸ್ 0 1 1 1 ಆಸ್ ಇಟ್ ಇಸ್ ಇರ್ತದೆ. ಸೊ ಏನಾಗ್ತದಲ್ಲೇ ವಾಟ್ ಎವರ್ ದ ಜನರೇಟೆಡ್ ವ್ಯಾಲ್ಯೂ ಇಸ್ ದೇರ್. ಸೊ ದಿಸ್ ಯು ಕ್ಯಾನ್ ಸಿ ಇಲ್ಲಿ ಐದರ್ 1 ಆರ್ 0 ಏನ್ ಜನರೇಟ್ ಆಗಿರ್ತದಲ್ಲ ಇದು ಔಟ್ಪುಟ್ ಹೊಳ್ಳಿ ಮತ್ತೆ ಸಕ್ಸೆಸಿವ್ ಅಪ್ರಾಕ್ಸಿಮೇಷನ್ಗೆ ಹೋಗ್ತದೆ ಇಲ್ಲಿ. ಸೊ ದ್ಯಾಟ್ ಈಸ್ ಅಪೆಂಡೆಡ್ ಆಸ್ ಅನ್ MSB bit. That is updated as an output bit is updated as an MSB bit. The remaining all bits are shifted one position next. So initially we had 0 and all the this no. So now what will happen? The output generated will be there. Then next this 0. Then this 1 1 will be there. 1 1 1 1. So this one will be shifted out. So like this it is gone comparing. So that's why this feedback, this is very important, this value. That's why what he has given, you see there, this is D7. So 0, 1 1 has come here and these 4 zeros. This gives the next approximation as D7 0 1 1, then next, which is either 1/4 or 3/4 of the full scale voltage depending on D7 bit here. Depending on the D7. The advantage of the successive approximation, the advantage, the advantage of the successive approximation ADC over the flash ADC is that it requires significantly fewer analog components, just one comparator. Where there ಅಲ್ಲಿ ಕಂಪ್ಯಾರಿಟರ್ ಎಷ್ಟಿರಬೇಕು, n ಬಿಟ್ ಐತಂತಂದ್ರೆ 2⁻n - 1 ಕಂಪ್ಯಾರಿಟರ್ಸ್ ಬೇಕಾಗ್ತಿದ್ವು ಅಲ್ಲಿ, ತಿಳಿತಾ? ಸೊ ಇಲ್ಲಿ ಬರೀ only one comparator and a DAC will do the job. So significantly the hardware required is reduced here. Right? So that is the advantage of successive approximation. But the disadvantage, however, is that more time is required to convert the value if the input signal changes by more than the precision of the ADC. While the ADC is making the successive approximation, we need to sample and hold the input. So convert ಮಾಡತ್ನಾಗನೇ value change ಆತಂತಂದ್ರೆ then what you have to do, whatever the sample value will be there, that you have to separately keep. So sample and hold circuit to digital ನಾಗ ಓದಿರ್ತೀರಿ ನೀವು. So there you have to keep the new data what is coming to the ADC there. Another disadvantage of successive approximation ADC is that the amount of digital circuitry required for implementation of the SAR. ನೋಡ್ರಿ, one comparator one DAC ಬೇಕು, but initially SAR register ಬೇಕಾ ನಿಮಗೆ? So that SAR register is an additional circuitry required. So ಎಲ್ಲಾದ್ರಿಗೂ ಹೆಂಗಿರ್ತದಂತಂದ್ರೆ always there will be a trade off. ಒಂದು ಅಡ್ವಾಂಟೇಜ್ ಇತ್ತಂತಂದ್ರೆ ಒಂದು ಡಿಸ್ಅಡ್ವಾಂಟೇಜ್. ಸೊ ಯು depending on our application what is needed, right? So how much we can invest on the embedded design what we are doing. So looking at all those things you should have, right? ಈಗ ನೋಡ್ರಿ ಏನಂತಂದ್ರ ಸರ್ಟನ್ ಎಂಬೆಡೆಡ್ ಅಪ್ಲಿಕೇಶನ್ಸ್ನಾಗ ಅನಲಾಗ್ ಟು ಡಿಜಿಟಲ್ ಕನ್ವರ್ಟರ್, ಡಿಜಿಟಲ್ ಟು ಅನಲಾಗ್ ಕನ್ವರ್ಟರ್ ಬೇಕಾಗೇ ಇರಂಗಿಲ್ಲ. ಅಂತ ಇದ್ರಾಗೆ ನಾವು ವಿ ನೀಡ್ ನಾಟ್ ಯೂಸ್ A to D D to A ಕನ್ವರ್ಟರ್ಸ್ ಬೇಕಾಗಿಲ್ಲ ಅಲ್ಲಿ. ಈಗ ಮೋಟರ್ನಾಗ ನೀವು ವಾಷಿಂಗ್ ಮೆಷಿನ್ನಾಗ ನೋಡ್ರಿ, ಜಸ್ಟ್ ಡ್ರೈವಿಂಗ್ ದ ಮೋಟರ್ ಕ್ಲಾಕ್ ವೈಸ್ ಆಂಟಿ ಕ್ಲಾಕ್ ವೈಸ್ ಸಾಕಲ್ಲಿ. ಸೊ ಡೈರೆಕ್ಟ್ಲಿ ಮೈಕ್ರೋ ಕಂಟ್ರೋಲರ್ ಇಂದ ಡೇಟಾ ಕಳಿಸಿ ಮೋಟರ್ ಕಂಟ್ರೋಲ್ ಮಾಡ್ಬೋದು ನೀವು. ವೇರ್ ಆಸ್ ಓವನ್ನಾಗೆ ಕಂಪಲ್ಸರಿಲಿ ಟೆಂಪರೇಚರ್ ಕಂಟ್ರೋಲ್ನಾಗ ಅಲ್ಲಿ ಬೇಕಾಗ್ತದಲ್ಲಿ ಅನಲಾಗ್ ಟು ಡಿಜಿಟಲ್ ಕನ್ವರ್ಟರ್. ಸೊ ಡಿಪೆಂಡಿಂಗ್ ಆನ್ ದ ಟೈಪ್ ಆಫ್ ಅಪ್ಲಿಕೇಶನ್ ವೆದರ್ ಆನ್ ಚಿಪ್ A to D ಕನ್ವರ್ಟರ್ ಆರ್ D to A ಕನ್ವರ್ಟರ್ ಇಸ್ ರಿಕ್ವೈರ್ಡ್ ಆರ್ ನಾಟ್ ಅಂತ ಹೇಳಿ ನೀವು ವಿಚಾರ ಮಾಡಬೇಕಾಗ್ತದೆ. ಸೊ ಅಪ್ರಾಕ್ಸಿಮೇಟ್ ADC is, so apart from, no doubt that we said here it is having only one comparator and DAC, but again additional circuitry what required is that approximation successive approximation register there. So SAR, the amount of digital circuitry to implement the SAR, this is the additional circuitry for successive approximation ADC, right? So like this the trade-offs will be there. So depending on the application and depending on the investment, how much, what kind of embedded system you are going to design, depending on that, you are going to select the inputs and outputs. So that's why you observe in your laptops and general purpose computers and all, you have big keypads, right? Whereas so many keys will be there, right? 30, 40, 50 keypads will be there. Whereas if you see in your mobile phones or your TV remotes or AC remotes and all, nodidre only array of switches will be there, hardly less, some 5 to 6 keys only will be there, right? So that is the thing there. So that's about the input devices, right? So when you come for the next class, you need to write details about the analog to digital converters, different types. One is flash ADC and another one is successive approximation ADC with the figure and the explanation. Compulsorily question for 10 to 12 marks. The next output devices. Can anybody tell me any of the output devices? ಲಿಸ್ಟ್ ಹೇಳ್ರಿ, ಯಾವ್ಯಾವ ಔಟ್ಪುಟ್ ಡಿವೈಸಸ್ ಅದಾವು?
Monitor,
ಓಕೆ
printers,
ಓಕೆ,
LEDs,
ಯಾ ವೆರಿ ಗುಡ್. ಮತ್ತೆ ಇನ್ನೊಂದೆರಡು ನಾವು ಬಹಳ ಓದಿವಲ್ಲ ಲಾಸ್ಟ್ ಕ್ಲಾಸ್ನಾಗೆ, ಇಲ್ಲಿ ಡಿಸ್ಪ್ಲೇಸ್ನಾಗೆ ಎಷ್ಟು ಬಂದತ್ತದು, ಇನ್ನೊಂದು ಯಾವುದು? LED ಮತ್ತೆ LED ಮತ್ತೆ ಯಾವುದು? LED and what else?
LCD display.
LED, LCD ಡಿಸ್ಪ್ಲೇ ಮತ್ತೆ 7 ಸೆಗ್ಮೆಂಟ್ ಡಿಸ್ಪ್ಲೇಸ್ ಎಷ್ಟು ಓದಿದ್ವಲ್ಲ, ಹೌದಾ?
Yes, ma'am.
So all these are the some of the examples of output devices. So output devices, first one is indicator lights. So the most common output devices are indicator lights that display on off or true or false information. So on off ಅಂತರ ನೀವು ಇದನ್ನ ಮಾಡ್ಬೋದು, ಇಂಟರ್ಪ್ರಿಟ್ ಮಾಡ್ಬೋದು, ಅಥವಾ ಲಾಜಿಕ್ ಲೆವೆಲ್ನಾಗ ಹೇಳ್ಬೇಕಂತಂದ್ರೆ you can interpret as either true or false also. An indicator might show whether a mode or a mode of the operation is either active, system is busy, or an error condition has occurred. The simplest form of the indicator is a single light emitting diode, that is LED. So it's a low cost, high reliable, and easy to drive from a digital circuit as shown in the figure. So the simplest form of output device is LED. So you can see there. So LED, right? Diode symbol with the two indicators. If you show, that will be an LED. So plus V is applied here. So this is the current limiting resistor is there. Then that is connected to an output driver circuit. So bubble is indicated here. That means it is active low. So which is connected to the cathode here, right? So the output circuit for an LED indicator. So always we use the current limiting resistor there. Otherwise directly the high voltage whatever is coming, it might destroy your device. So that's why we always use the current limiting resistors. So when the output from the driver is in low voltage, so that's why bubble is shown. So he is telling, see here, the bubble is shown, that is low voltage. The current flows through the LED causing it to turn on. The resistor limits the current so as not to overload the output driver or the LED. So basically the resistor is used for current limiting, right? We choose the resistance value to determine the current and hence the brightness of the LED. So this is going to decide the brightness of the LED, current limiting resistor. When the output from the driver is high voltage near the supply voltage, the voltage drop across the LED is less than its threshold voltage. So no current flows, hence the LED is turned off. So this operation on the LED ಎಲ್ಲರಿಗೂ ಗೊತ್ತೈತೆ, turned off. So for example, you can see, determine, all of you do this, Determine the resistance for the LED pull-up resistor. R value ಕಂಡುಹಿಡಿಬೇಕು ನೀವು. Pull-up resistor connected to a 3.3 volts power supply. Power supply given is 3.3 volts. The LED has the forward biased voltage drop of LED nagu voltage drop. So LED will eat the supply voltage nag LED ಎಷ್ಟು ತಿಂತತಿ? LED will eat 1.9 volts and it is sufficiently bright when the current flown is 2 milliamperes. So what should be the current limiting resistance? So tell me. So 3.3 volts is the power supply, 1.9 volts and 2 milliamperes. Right? 2 milliamperes current. Then input voltage is how much? 3.3 volts. And LED is going to eat how much? 1.9 volts, right? So what should be the value of the resistance? So quickly tell me. Are you calculating in your notes, all of you? Sumalata, Vasudev Reddy, Shivani, Sandhya, Sai Kalyan, Ankita, Navya.
700 volts, ma'am. 700 ohm, ma'am.
700 ohms, huh?
Yes, ma'am.
Others, any other value?
Same, ma'am. 700 ohm.
Okay. Simple it is. So you can see here. Assuming the output driver low voltage, so 700 ohms. Most of you have calculated this right. Okay, 3.3 minus 1.9, 1.4 volts. So V is equal to IR, R is equal to V by I. So 1.4 by 2 milliamperes. So you'll get as 700 ohms. But what he is telling, the closest standard value is ನಿಮಗೆ ಯಾವ ರೆಸಿಸ್ಟೆನ್ಸ್ ವ್ಯಾಲ್ಯೂ ಬೇಕು ಹಂಗೆ ರ್ಯಾಂಡಮ್ ಆಗಿ ಸಿಗಂಗಿಲ್ಲ. ಸೊ ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಓನ್ಲಿ ಯು ಶುಡ್ ಟೇಕ್ 1K 2K 10K ರೆಸಿಸ್ಟೆನ್ಸಸ್ ಹಂಗೆ ಚಿಕ್ಕದು. he is telling 680 ohms only is the available resistance that you can use. Okay, good, all of you. So that is regarding the LED. Then next one is 7 segment display. How many times we have got 7 segment display? So next is 7 segment display. So I had told you 2 types of 7 segment displays will be there, right? Common anode and common cathode. ಈ ಫಿಗರ್ ಕೂಡ ನಾನು ಎಷ್ಟು ಸರ್ತಿ ಡ್ರಾ ಮಾಡಿ ತೋರಿಸಿದ್ದೆ ನಿಮಗೆ. ABCDEFG, right? So common anode, all the anodes are connected and you are going to illuminate each one. So A ಆನ್ ಮಾಡ್ಬೇಕಂತಂದ್ರೆ A ಗೆ ಏನು ಹೋಗಬೇಕು? ಹೈ ಹೋಗಬೇಕಾ ಝೀರೋ ಹೋಗಬೇಕಾ? ಹೈ ಹೋಗಬೇಕಾ ಝೀರೋ ಹೋಗಬೇಕಾ? Cathodic connect agitadu. So whether it is active low signal or active high activated. A value ಏನು ಕಳಿಸ್ಬೇಕು ನೀವು? A LED ಆನ್ ಆಗ್ಬೇಕಂತಂದ್ರೆ ಇಲ್ಲಿ ಏನು ಕನೆಕ್ಟ್ ಆಗ್ಬೇಕು ಇಲ್ಲಿ A ಗೆ? 0 ನಾ 1 ನಾ? How much time you people are taking? Full silent ಕುಂತು ಬಿಡ್ತೀರಿ. A 0 ಇರಬೇಕಾ 1 ಇರಬೇಕಾ? If anodes all are connected to high there, common anode all will be connected to high. So each one ಯಾವ್ದರ ಫಿಲಮೆಂಟ್ ನೀವು ಈಗ ಇದನ್ನ ಆನ್ ಮಾಡ್ಬೇಕಂತಂದ್ರೆ ಹೇಗೆ ಏನು ಕನೆಕ್ಟ್ ಮಾಡಬೇಕು? ಈಗ ಎ LED ಆನ್ ಆಗ್ಬೇಕಂದ್ರೆ ಏನು ಕನೆಕ್ಟ್ ಮಾಡಬೇಕು? 0 ನಾ 1 ನಾ? ಆಕಾಶ್,
1.
1 ಯಾಕೋ? ಇದೇನಿದೆ ಸಿಂಬಲ್? ಇದು ಕ್ಯಾಥೋಡ್, ಇದೆ ಆನೋಡ್. ಇದನ್ನ ಏನಂತಂದ್ರ ಒನ್ ಕನೆಕ್ಟ್ ಮಾಡಿದ್ರೆ ಏನಾಗ್ತತಿ ಇದು ಆಕ್ಟಿವೇಟ್ ಇದನ್ನ ಆಗ್ತತ ಫಾರ್ವರ್ಡ್ ಬಯಾಸ್ ಆಗ್ತತ ರಿವರ್ಸ್ ಬಯಾಸ್ ಆಗ್ತತ ಅಲ್ಲಿ +5 ವೋಲ್ಟ್ಸ್ ಕನೆಕ್ಟ್ ಮಾಡಿದ್ರೆ ಇದು ಫಾರ್ವರ್ಡ್ ಬಯಾಸ್ ಮಾಡ್ಬೇಕಂತಂದ್ರೆ ಏನ್ ಮಾಡ್ಬೇಕು ದಿಸ್ anode has to be connected to positive whereas cathode has to be connected to negative. ಇಲ್ಲಿ 0 ಕಳಿಸಿದ್ರೆ ಮಾತ್ರ each particular LED will be activated. Yes, so this has to be connected to what common anode. All the anodes will be connected to positive whereas +5 volts, whereas this will has to be connected to 0 volts. So whichever you want to ಇದನ್ನ lead, that particular has to be connected to 0. So depending on that only think ನಾವು ಇದು ಈಗ ನನಗೆ ಇದು ಒಂದೇ ಇದನ್ನ ಮಾಡ್ಬೇಕಂದ್ರೆ ಇದು 0 ಇನ್ನು ಉಳಿಕಿದ್ದೆಲ್ಲ 1 1 1. So depending on common anode or common cathode we are sending these values. ತಿಳಿತಾ? ಅಕಸ್ಮಾತ್ ಕಾಮನ್ ಕ್ಯಾಥೋಡ್ ಇದ್ದಿತ್ತಂದ್ರೆ all this would have been what is happening? Getting activated. ಅದೇ ಕಾಮನ್ ಕ್ಯಾಥೋಡ್ನಾಗೆ all will be connected together, right? And this will be connected to 0, right? And each anode you should be connecting to 1, right? So depending on that, because this is anode, so forward bias agಬೇಕಲ್ಲ, so that time it will be done. If you doesn't want to lit, then it has to be connected to 0, so that this will be reverse biased, right? ಇಲ್ಲಿ ಅದೇ ಈ ಕಾಮನ್ ಆನೋಡ್ನಾಗ ಏನಾಗೈತಿ, ಕಾಮನ್ ಆನೋಡ್ನಾಗ ಏನಾಗೈತಿ, ಆಲ್ ದಿಸ್ ಆರ್ ಕನೆಕ್ಟೆಡ್, ದಿಸ್ ವಿಲ್ ಬಿ ಕನೆಕ್ಟೆಡ್ ಟು ಹೈ ಓನ್ಲಿ, ರೈಟ್? ಅಂಡ್ ಡಿಪೆಂಡಿಂಗ್ ಆನ್ ದಟ್ ಯಾವ್ದು ನಿಮಗೆ ಇದು ಮಾಡಬೇಕು, ಡಿಪೆಂಡಿಂಗ್ ಆನ್ ದಟ್ ಯು ಆರ್ ಗೋಯಿಂಗ್ ಟು ಸೆಂಡ್ 0. ಸೊ ದಿಸ್ ಇಸ್ ಕ್ಯಾಥೋಡ್ ಹಿಯರ್. So thus what will happen, this particular it is going to act as a closed switch. So this is going to be activated. So depending on whether it is common anode or common cathode, we are going to send either 1 or 0. Is it clear to you all? Akash, clear aita?
Yes, ma'am.
So like this, so you can see there, till now we had seen only connection of only one 7-segment display. Oh, that 4 7-segment display counter also we had done, no, one example. So here, that's why how many LEDs are being shown here? So 4 LEDs, 4 7-segment displays, 1 2 3 4. So connection of 7-segment LEDs in a common anode 7-segment display, common anode type idu. So connection of 4 7-segment display digits, 4. So you can see there, these 4 are connected to where transistors, right? So depending on all the emitters are connected high here, so depending on that, so input see there A3 bar, A2 bar, A1 bar and A0 bar. Depending on this signal, so these 7 segments are controlled, right? So whichever signal is activated, depending on that, each segment will be each 7-segment display will be activated. Again in 7-segment display, each segment is having one LED here. So this is A, B, C, D, E, F and G. So again these are connected to all this here, A, B, C, D, E, F, G, and you have the parallel connection. So parallel connection to each, right? So depending on that, we are going to send the data here. See there, A bar, B bar, C bar, D bar, E bar, F bar, G bar. That means I am going to send 0. If I want to lit A here, then I have to send 0 to A. Then total 7-segment nange ನಾನು ಇಲ್ಲಿ 0 ಡಿಸ್ಪ್ಲೇ ಮಾಡ್ಬೇಕಂತಂದ್ರೆ, ಈ 0 ಡಿಸ್ಪ್ಲೇ ಮಾಡ್ಬೇಕಂತಂದ್ರೆ n number of times I have told A, B, C, D, E and F. ಇವೆಲ್ಲ LEDs ನಾನು 0 0 0 ಕಳಿಸ್ಬೇಕು, ಎಲ್ಲಕ್ಕೂ 0 ಕಳಿಸ್ಬೇಕು, ಬರೀ ಇದು ಒಂದಕ್ಕೆ ಮಾತ್ರ 1 ಕಳಿಸ್ಬೇಕು. Then I am going to display 0 here. This I have told a number of times. Is it okay to you all? Depending on that only the code is generated. 0, 0, 0, 0, then 0, 0, 0, 1. So this will be the code sent to display 0 there to 7 segment. That too, after you send this value here, again this has to be activated by this fellow also. A naught also here, if I have sent 0, then on this 7 segment display 0 is displayed, right? 0 is displayed. So like this we are going to control using these lines, right? So I think so this is fourth time fourth program what we are doing is with 7 segmented display, I think. Okay, to display several digits, for example an alarm clock. ಇದ್ರಾಗ ಸಹಿತ ನಾವು ಏನಂತಂದ್ರೆ ಅಲ್ಲೇನು 4 digits alarm clock ನಾಗ ಅಂತಂದ್ರೆ 4 digits will be there. So to display several digits, for example an alarm clock has 4 digits for the hours and the minutes of the time. So the connections for the LEDs in each digit with common anodes, see there, yellow common anode are shown in the figure. In addition to the 7 LEDs for the segments, there is an LED for the decimal point also. ಇವು 7 ಸೆಗ್ಮೆಂಟ್ 1 2 3 4 5 6 7 ಇವು 7 ಸೆಗ್ಮೆಂಟ್ ಅಲ್ಲದೆ ಡೆಸಿಮಲ್ ಪಾಯಿಂಟ್ ಅವರ್ಸ್ ಆದ್ಮೇಲೆ ಇಂಡಿಕೇಟ್ ಮಾಡಕ್ಕೆ ಇವು ಡಾಟ್ಸ್ ಅದಾವಲ್ಲ, this decimal point DP, this is also used along with the 7 segments, right? So the connections for the LEDs in each digit with common anodes are shown in the figure. In addition to the 7 LEDs for the segments, there is an LED for the decimal point also. The output connections for the 4 digits are shown in figure. Each of the outputs are A0 through A3, not of A0, that is active low enabled. When pulled low, turns on the transistor that enables the digit. So transistor on ಆಗ್ಬಿಟ್ಟು ಆ particular digit ಅನ್ನ enable ಮಾಡ್ತದೆ ಅಲ್ಲಿ. So to display the 4 digits, we pull each of A0 through A3 low. So 4 digits ಅನ್ನ ನಾವು ಡಿಸ್ಪ್ಲೇ ಮಾಡ್ಬೇಕಂತಂದ್ರೆ ಎಲ್ಲ A0 to A3 should be turned in low, right? When A0 is low, enabling the least significant digit, we derive the segment lines A through G, not of A through G. ಎಲ್ಲ ನೋಡ್ರಿ, ಎಲ್ಲ ಆಕ್ಟಿವ್ ಲೋನೇ ಇರೋದ್ರಿಂದ, all are active ಲೋನೇ ಇರೋದ್ರಿಂದ, so depending on this A0, A1, A2 and A3, so these are all are activated for displays. Again, each display is activated through A0 through G there. That's what he is telling. To display 4 digits, 4 digits ಅನ್ನು ನಾನು ಡಿಸ್ಪ್ಲೇ ಮಾಡ್ಬೇಕಂತಂದ್ರೆ we pull all from A0 to A3 ಎಲ್ಲಾನು A0 to A3 ನಾಲ್ಕುನು ಕೂಡ 0 ಮಾಡಬೇಕು. All should be pulled low, then only this will be activated. A0 to A3 low in turn. So when A0 is low, enabling the least significant digit, we derive the segment lines, that is segment lines ಎಲ್ಲಿಂದ ಎಲ್ಲಿವರೆಗೂ A through G and one more is decimal point DP. So low or high as required for the segment pattern. Low or high ಹೆಂಗ್ ಚೂಸ್ ಮಾಡ್ತೀವಿ? 0 ಬೇಕಾದ್ರೆ ಒಂದು ಪ್ಯಾಟರ್ನ್, 1 ಬೇಕಾದ್ರೆ ಒಂದು ಪ್ಯಾಟರ್ನ್, 2 ಬೇಕಾದ್ರೆ ಒಂದು ಪ್ಯಾಟರ್ನ್. So depending on that pattern for that digit, ಆ digit ಏನು ಪ್ಯಾಟರ್ನ್ ಬೇಕು, depending on that this A through G are done. So when A1 is low, we derive the segment lines for the next digit and so on. Next ಅದೇ A2 is low ಅಂತಂದ್ರೆ, so A2 is low ಅಂತಂದ್ರೆ third digit, A3 is low ಅಂತಂದ್ರೆ fourth digit. So this will be the least significant digit, this will be the most significant digit, which is connected to A3 will be the most significant digit, right? So after driving the most significant digit, we cycle back to the least significant digit. If we cycle through the digits fast enough, our eyes persistence of the Vision smooths out any flickering due to each digit, only being active for 25% of the time. Actually, ಅಷ್ಟು ಫಾಸ್ಟ್ ಆಗ್ತಿರ್ತದಂದ್ರೆ actually ಒಂದಾದ್ಮೇಲೆ ಒಂದನೇ ಚೇಂಜ್ ಆಗ್ತಿರ್ತೈತಿ, but we see that everything is happening quickly. Persistence of the eye. The advantage of this scanned scheme is that we only need one signal for each digit plus one for each segment of the digit. For example, to drive 4 digits, we need 12 signals. Compared with the 32 signals we would need had we driven segments individually. ಒಂದೊಂದು ಸೆಗ್ಮೆಂಟ್ ಮಾಡಿದ್ರೆ ಎಷ್ಟು ಬೇಕಾಗ್ತಿತ್ತು, ರೈಟ್? ದಟ್ಸ್ ವೈ 8×4 32 separate lines ಬೇಕಾಗಿತ್ತು, ರೈಟ್? ದಟ್ಸ್ ವಾಟ್ he is telling. Compared with 32 signals we would need, ಈಗ ಇಲ್ಲಿ ಎಷ್ಟಾಗ್ಯಾವು? 8, 9, 10, 11, 12 ಇವೆಂಟು ವಿಚ್ ಆರ್ ಪ್ಯಾರಲಲಿ ಕನೆಕ್ಟೆಡ್ ಟು ದ ಸೆಗ್ಮೆಂಟ್ಸ್. ಆಮೇಲೆ ಇವು 4. ಸೊ 4 ಟು ಸೆಲೆಕ್ಟ್ ಬಿಟ್ವೀನ್ ದ ಡಿಜಿಟ್ಸ್. ಸೊ ಟೋಟಲ್ 8, 4, 12 ಸಾಕು. ಅದೇ ನಾನು ಒಂದೊಂದೇ ಸಪ್ರೇಟ್ 7 ಸೆಗ್ಮೆಂಟ್ ಮಾಡ್ಕೊಂಡಿದ್ನಂದ್ರೆ ಇದ್ರದ್ದು 8 ಲೈನು, ಇದ್ರದ್ದು 8, ಇದ್ರದ್ದು 8 ಟೋಟಲ್ 32 ಆಗ್ತಿತ್ತು. ಅದನ್ನೇ ಹೇಳಕತ್ತ ನಾನು. ಸೊ ಸಿ ದೇರ್, ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, to drive 4 digits we need only 12 signals. 4 signals to select the digits and 8 signals to select each filament of the digit is more than enough. Compared with 32 signals, 32 separate signals we would need if we would have driven the segments individually. 32 separate lines ಬೇಕಾಗ್ತಿತ್ತು. ಸೊ ಇಲ್ಲಿ ಪ್ಯಾರಲಲ್ ಕನೆಕ್ಷನ್ ಕೊಟ್ಬಿಟ್ಟು 8 ಕನೆಕ್ಷನ್ಸ್ ಫಿಲಮೆಂಟ್ ಸೆಲೆಕ್ಟ್ ಮಾಡಕ್ಕೆ, 4 ಡಿಜಿಟ್ಸ್ ಸೆಲೆಕ್ಟ್ ಮಾಡಕ್ಕೆ ಅಷ್ಟೇ. ಸೊ ಡಿಪೆಂಡಿಂಗ್ ಆನ್ ಅವರ್ ಅಪ್ಲಿಕೇಶನ್ ವಿ ಮೈಟ್ ಯೂಸ್ ಎ ಕೌಂಟರ್ ಆರ್ ಶಿಫ್ಟ್ ರೆಜಿಸ್ಟರ್. ಸೊ ಕೌಂಟರ್ ಅಥವಾ ಶಿಫ್ಟ್ ರೆಜಿಸ್ಟರ್ ಯೂಸ್ ಮಾಡಿಬಿಟ್ಟು ಟು ಡ್ರೈವ್ ದ ಡಿಜಿಟ್ ಎನೇಬಲ್ ಔಟ್ಪುಟ್ಸ್ and an 8-bit wide multiplexer to select the values to drive on to the segment outputs. So ನಾವು ಏನು ಮಾಡ್ಬೋದು, ಇಲ್ಲಿ ಕೌಂಟರ್ ಅಥವಾ ರೆಜಿಸ್ಟರ್, ಶಿಫ್ಟ್ ರೆಜಿಸ್ಟರ್ ಯೂಸ್ ಮಾಡಿಬಿಟ್ಟು ಡಿಜಿಟ್ಸ್ ಸೆಲೆಕ್ಟ್ ಮಾಡೋದು. ಆಮೇಲೆ ಮಲ್ಟಿಪ್ಲೆಕ್ಸರ್ ಯೂಸ್ ಮಾಡಿಬಿಟ್ಟು ಇದನ್ನ ಏನಂತಂದ್ರೆ ಈಚ್ ಫಿಲಮೆಂಟ್ ಅನ್ನ ಕಂಟ್ರೋಲ್ ಮಾಡಬಹುದು. So there is an example. See there all of you. Develop a VERILOG model. Develop a VERILOG model of display multiplexer and decoder for 4-digit 7-segment display shown in the figure. The circuit has 4 BCD inputs. The decimal point for the leftmost digit should be lit. Leftmost digit ಗೆ decimal point lit ಆಗಬೇಕು and the remaining decimal points not lit. ಅಂತಂದ್ರೆ ಇದು leftmost ಯಾವ್ದೈತಲ್ಲ ಇದು ಒಂದೇ, this one out of 4 digits the leftmost DP should be lit. For others it should not be lit. So the decimal point for the leftmost digit should be lit and the remaining decimal points not lit. The system clock has a frequency of 10 megahertz. So you will have to write the VERILOG model for that. So the VERILOG code is there. So you write and come. Try to understand. Already this n number of times we have done. Only change is here. You need to select between the 4 digits, that's all. So only that change will be there. Whereas other, to displaying that BCD 0 to 9, the 7-segment code is the same as that we have done in the earlier classes. So you write the code and come. We'll discuss once in the next class. All right? Is it clear to you all of you?
Yes, ma'am.